In this math talk, I'm going to develop the derivative of the inverse cotangent function, and to do that I'm going to split this into two videos. In the first, I'm going to discuss the meaning of the inverse cotangent, because that's sometimes a bit fuzzy for students, and then I'll follow that with the development of the actual derivative using algebra and some work with right triangles. The second video that I do will be optional for viewing, but I strongly encourage it because I will examine that derivative graphically. And through that examination, I think you'll develop a much better understanding and intuition as to why the inverse cotangent derivative looks like it does. Now, to follow along with this tutorial, you really need to be pretty comfortable with your trig ratios, and those are both the primary and the reciprocal trig ratios as they're defined for right triangles and angles in standard position. You need to already know the derivative of the cotangent function, and you have to be comfortable with implicit differentiation. Now, why did I choose to do this particular function? Why am I differentiating this function? Well, I've got a really cool application that I'm going to do after this video that I'm hoping will forever change where you decide to sit in a movie theater. And yes, it involves the inverse cotangent function. So let's begin. What is it that I mean when I say theta equals cotan inverse of root 5 over 3? What does that actually mean? Well, I'm saying that an angle theta exists whose cotangent is root 5 over 3. And so if we go to our definition of cotangent, cotangent is the reciprocal of tangent, 1 over tangent, tangent being opposite over adjacent in a right triangle. That makes cotangent adjacent over opposite, or when we talk about an angle in standard position, x over y. If we were to draw that in a diagram, theta would be the angle sitting here, this acute angle, with an adjacent side that is root 5 and an opposite side that is 3. So in a nutshell, I'm saying theta equaling cotan inverse of root 5 over 3, theta is an angle whose cotangent is root 5 over 3. And to me, the most important part of that is that when you see an inverse cotangent, you are talking about an angle, not a trig ratio. This is really just an angle whose cotangent is root 5 over 3. Well, that sets us up to talk about what is meant by y equals cotan inverse of x. Well, again, I say that y is actually an angle. Y is the angle whose cotangent is x, or you could write it as cotangent y is x over 1. That would allow you to construct a triangle, again with an acute angle y, an adjacent side that is x, and an opposite side that is 1. Now, in order to complete that triangle, to find the hypotenuse, I will use the Pythagorean theorem. C squared would be equal to 1 squared plus x squared. That's just your Pythagorean theorem using the two legs of the right triangle. That turns into c squared equaling 1 plus x squared, or c equaling the square root of 1 plus x squared. So with that expression in for my third side, I'm ready now to develop the derivative of the inverse cotangent. And so in the process of differentiating this, I just want to highlight that what we're trying to find is how y changes with x. That's what derivatives do. They tell you how y changes with respect to x. So in other words, I'm really asking the question, how will angle y increase or decrease as I lengthen and shorten x? And I think even with that sort of thought process, I think intuitively or in your mind's eye, you can visualize what is probably going on. As I lengthen x and keep the opposite fixed at 1, what will happen to angle y? But I'll let you think about that. We'll examine that really in quite a bit of detail in the graphical interpretation of this. So now, I'll begin by saying y equals cotan inverse of x, and I will rewrite that as cotan y equals x. Next, I need to differentiate both sides with respect to x, and this is where the implicit differentiation comes into play. I'm taking a function cotangent y and I'm differentiating with respect to variable x. From implicit differentiation, we know that we must first differentiate the cotangent y function with respect to y and then multiply by dy by dx. So on the left-hand side, the derivative of cotangent y with respect to y is negative cosecant squared y. And then I multiply by dy by dx. On the right-hand side, the derivative of x with respect to x, well, that's just a constant, 1. Now we're trying to isolate for dy by dx. We do that by dividing both sides by this negative cosecant squared y. So we'll divide by negative cosecant squared y. On the left-hand side, I'll be left simply with dy by dx. On the right-hand side, I will have negative 1 divided by cosecant squared y. Now, I'm going to use the definition of cosecant to help me simplify this derivative further. So I know that cosecant y is the same as 1 over sine y, or alternatively, I can say 1 over the cosecant y is equal to sine of y. They are reciprocals of each other. And then I can further say that 1 over cosecant squared y is sine squared y. So I'm going to take the entire 1 over cosecant squared y and replace it with sine squared y. At this point, I'm almost finished my derivative. I'm going to have to return to my triangle, though. I would write dy by dx equals negative sine y all squared, and then look at my definition of sine of an angle in a right triangle. It's opposite divided by hypotenuse. So when I look at sine of y in this triangle, the sine of y is the opposite divided by the hypotenuse. So I would write dy by dx equals negative 1 divided by the square root of 1 plus x squared. To finish this off, I just need to square the numerator and the denominator of this fraction. Squaring the numerator will produce just a 1, and the denominator, squaring it, removes the square root. So I actually have just a nice clean expression that says the derivative of my cotangent inverse function is simply negative 1 over 1 plus x squared. Or in more general terms, we would say the derivative with respect of cotangent inverse of u, where u is some other function within the cotangent inverse function, I would get negative 1 over 1 plus that function squared times the derivative of that function. So now let's try a few of this form. Beginning with d by dx of cotangent inverse of 5x, I would write negative 1 over 1 plus, and I would take that function and square it in the denominator and multiply by the derivative of the 5x, which would be 5. Multiplying the numerators, I get negative 5 over 1 plus, and then squaring this term in the denominator, I get 25x squared. Trying it again with the derivative with respect to x of cotangent inverse of x cubed. Once again, negative 1 divided by 1 plus, and this function needs to be squared. So x cubed squared times the derivative of that function, which is 3x squared. Multiplying numerators, I get 3x squared. In the denominator, I get 1 plus x cubed squared is x to the 6. Now the last one seems a little bit odd, but I'm doing it to set us up for the work on the movie theater question. So I'm going to take the derivative with respect to x of cotangent inverse of x over a. And in this particular case, a is a constant. A is a constant. So once again, it's negative 1 over 1 plus this function squared times the derivative of the x over a. So the derivative of x over a is just going to be 1 over a. Now expanding the numerators, I get negative 1. On the denominator, I expand the a with the 1 to get a. And the a with this expression squared looks a little bit like this. X squared over a squared times a. The a's will reduce to produce x squared over a. So I have negative 1 over a plus x squared over a. That's still a little bit awkward, so I'd multiply top and bottom again by an a, producing in the numerator negative a. Then the a times the a here would give me a squared. The a times the x squared over the a reduces again, just leaving me with an x squared. And so that's my finished derivative. That's all the time I have. Thanks for watching. We'll see you in the next video.